Okay, good afternoon, ladies and gentlemen. So as head of the Department of Applied Mathematics and Theoretical Physics, I'd like to welcome you here to the third Andrew Chamblin Memorial Lecture. The first lecture was given 2 years ago by Stephen Hawking, and the second lecture last year by Roger Penrose. And we're very pleased that today we have Professor Paul Davies from Arizona State University to give the third lecture. So before introducing Professor Davies properly, I'd just like to say a few words about Andrew Chamblin, in whose memory this lecture series has been established. Andrew was born in Lubbock, Texas, and he attended Rice University, where he majored in mathematics. He then came to the UK, and he spent the year 1991 to 92 at Christ Church, Oxford, studying twistor theory and global methods in general relativity with Roger Penrose. He then moved to Cambridge, where he worked. He was a PhD student at St John's and also in DAMPT in my department, and he worked under the joint supervision of Gary Gibbons and Stephen Hawking. And this is a nice picture of theoretical physicists doing what theoretical physicists do, which is eat lunch in exotic parts of the world. So whilst Andrew was in DAMPT, his interests turned from twistors to classical relativity, to quantum gravity, and to the newly emerging M theory. Over his career, he made several important research contributions and published over 50 papers, indeed delivered many talks and lectures around the world. After he completed his PhD, he moved to, he became the Dreyfus Research Fellow at Pembroke College, and then he moved to other posts at Santa Barbara, at MIT, Los Alamos, and Queen Mary College. And ultimately, he was appointed as an assistant professor at the University of Louisville in Kentucky. And it was there that he sadly died unexpectedly on the 6th of February 2006 at the age of 36. Andrew's many friends and collaborators in DAMPT and around the world were very sad to hear his untimely death. And we in DAMPT were greeted warmly the idea that a fund might be set up to support a series of lectures to perpetuate Andrew's memory and promote the broad area of science in which he was interested. Dr. Joe Ashbourne, who's here today, and Andrew's family have been the prime movers in the establishment of this fund. And donations have come from Andrew's family and personal friends, and from many theoretical physicists across the world. And the fund now has sufficient money that we can have an Andrew Chamblin Memorial Lecture every year in perpetuity. Andrew's parents, who sadly can't be here today, commissioned a fine bust of Andrew, which we have cited in our department. So each year this lecture will serve as a chance to remember Andrew as a theoretical physicist who had achieved a great deal in his short career, and also to many as a friend, as a missed colleague and friend. So I'd now like to move to introducing our lecturer today, who is Professor Paul Davies, who is widely known as a theoretical physicist and cosmologist, and also particularly as an author and broadcaster who's brought many fundamental topics in science to a wider public. Professor Davies was a PhD student at University College London, where he first worked on radiation emission in electron-ion interactions, which was important in atomic astrophysics. His interest broadened, and after completing his PhD, he moved here to Cambridge to the Institute of Astronomy, perhaps a move that was perhaps helped by the fact that Fred Hoyle, who was the director of the Institute, was his PhD examiner. Professor Davies then later moved to King's College London, and then took up a chair of theoretical physics at the University of Newcastle in 1980. And over this period, he made many important contributions to understanding problems of quantum theory, radiation, thermodynamics, and black holes. He started writing books, and his first book, aimed at a popular audience, was The Runaway Universe, which was published in 1978, and he's subsequently written many more books, more than 20. In 1990, he moved to the University of Adelaide, and then later to Macquarie University, where he helped found the Australian Centre for Astrobiology, reflecting his increasing interest in the origins of life. And since 2006, he's been based at Arizona State University, where he's director of Beyond, which is a centre for fundamental concepts in science. The importance and impact of Professor Davies' books have been acknowledged by various awards, by the award of the Kelvin Medal from the Institute of Physics, the Faraday Prize of the Royal Society, and in fact predating those in 1995 the Templeton Prize, The Templeton Prize was established by the late Sir John Templeton in 1972 to identify what he called entrepreneurs of the spirit, outstanding individuals who've devoted their talents to expanding our vision of ultimate purpose and reality. In the last 2 decades, the prize has been awarded to several theoretical physicists, but Professor Davies was one of the first, I think, to receive the award. So the title of his talk today is How Many Universes Are There? And so please will you join me in welcoming Professor Davies as the third Andrew Chamblin Memorial Lecturer.
Dr. Ashbourne, friends of Andrew Chamblin, ladies and gentlemen. I wish I could claim a close contact with Andrew, but the closest connection that I can discern is that I have a cousin who lives in Louisville, Kentucky. For my own part, as you just heard, I now live in Phoenix, Arizona, and about 100 miles to the north is the town of Flagstaff. It was in Flagstaff in the 1890s that a rich and somewhat eccentric astronomer, Percival Lowell, built an observatory to study the canals of Mars. Unfortunately, the canals turned out to be a figment of Lowell's imagination, but a few years after the observatory was built, a young astronomer by the name of Vesto Slipher began a series of remarkable and careful examination of the light from nearby galaxies. Exactly 100 years ago, he embarked on measuring the quality of that light, and here's a picture of him at the telescope in Flagstaff. And he was able to discern the fact that other galaxies have their light systematically shifted towards the red end of the spectrum. This is something that is now part of popular parlance. We call it the red shift. And Slipher's observations became the basis of the work by the better-known astronomer Edwin Hubble, lawyer-turned-astronomer, who in the 1920s assembled the data from the redshift of galaxies systematically across the universe, and from that drew the conclusion that the universe as a whole is expanding. So this is a picture from the eponymous telescope, the Hubble Space Telescope, the so-called Hubble Deep Field. Each one of those dots is a galaxy, and this telescope can probe something like 12, 13 billion light years out into space, and all those far-flung galaxies are rushing away from us in a systematic pattern that is best described by saying that the universe is expanding. Some people have difficulty in understanding that concept. One way that can help is to think of the space between the galaxies as swelling or stretching, rather than the galaxies all rushing away from some common center. The main point I want to make is that if the universe is getting bigger, then it must have been smaller in the past. And the early astronomers concluded that if you ran the great cosmic movie backward, there must have been a time some billions of years ago when everything was squashed together in one place, and this suggested that the universe erupted from some highly dense condition billions of years ago, and we now call that eruption event the Big Bang. I should say, seeing as Fred Hoyle's name has already been mentioned, and I always feel I should put in a good word for Fred because he gave me my first real job here in Cambridge in 1970, that it was he who coined this term Big Bang, but he coined it as a term of derision because he didn't believe in the Big Bang. He had an alternative theory, the so-called steady-state theory of the universe, according to which it had no beginning and will have no end. And he sort of shrugged aside the idea of the universe bursting into existence a finite moment in the past by saying somewhat derisively, some people think it begins with a Big Bang. But the name has stuck, and that's what almost all cosmologists today would say happened, that the universe, at least as we know it, began with a gigantic explosion. Now, Normally I try to avoid saying what I do when at dinner parties, but if it's dragged out of me and I mutter scientist, and then if I mutter cosmology, you can bet that within a minute or so somebody will round on me saying, well, you scientists are all very clever, but what happened before the Big Bang? With a sort of, aha, that's got you stumped, looked. Well, of course, it would be a poor cosmologist who hadn't addressed that issue. So if we think that the universe began with a Big Bang, inevitably it begs the question, what happened before? Now, let me try and unpack this whole concept of before the Big Bang. One way we can think about this, if we assume that the universe didn't exist forever, if it came into existence, one way we can think about it is in terms of time stretching back for all eternity, and there'd be some moment, C, for creation if you like, and there'd be before creation when there wouldn't be a universe, and after creation when there is a universe. So that seems like a simple picture, and it's the sort of picture most people have in mind, and I suppose it's the sort of picture that most people had in mind for hundreds, if not thousands of years. But it comes with a problem. What we would like to know caused this event to happen, this origin of the universe event, this creation event. What brought it about? Well, we can think of two broad classes of answers. One is that some sort of physical process acted to bring it about, and the other is that some supernatural process, God, if you like, acted to bring it about. Now, both of these run into difficulties. If it was a physical process, we can always ask, well, why did the process happen at that particular moment in time? After all, if time stretches back for all eternity, and for an infinite amount of time nothing happened, why should suddenly something go bang and make a universe? On the other hand, if it was God who did it, then what was God doing before making the universe? Now, the standard answer to that used to be busy making hell for the likes of you. And so this was a common taunt that pagans made of the early Christians, and a more satisfactory answer was produced by Augustine of Hippo in the 5th century. And he said, somewhat presciently, that the world was made with time and not in time. And this completely changes the character of the problem. So now you see the diagram has time going back to this creation event, but before it is nothing, not just no matter, but no space and no time, no thing whatsoever. So in this simple picture of Augustine in the 5th century, all physical existence began at this moment I'm calling t equals 0. The originating event was not just the appearance of matter, but space and time as well. So there was no time before the origin of the universe, according to this picture. So the question about what caused the origin of the universe, or what happened before it, simply becomes meaningless. Now, if you trot this out at dinner parties, you can be sure that you will be accused of some sort of intellectual trickery, because people still want to know why the universe came into existence. Why did this thing happen? Now, of course, scientists are not supposed to ask why questions. And when I was a student, which is decades ago, as you can deduce, back in the 1960s, it was assumed that there was a Big Bang, but that the event itself, the originating event, was beyond the scope of science. It was simply not possible to give any sort of scientific explanation. You simply accepted it as a brute fact. It just happened. But we're not prepared to put up with that, and so inevitably cosmologists began to think about, could we bring the origin of the universe itself within the scope of scientific inquiry? And the way forward was because of an increasing belief that quantum physics had something to say about the very early universe. Now, quantum physics has a much more subtle arrangement between cause and effect, and it's one that's beyond the scope of this lecture. I simply want to say that it opens the door to a more sophisticated analysis of the notion of causation. But the point I want to make, that I'm going to be focusing on, is that if, as a result of some more sophisticated analysis, the origin of the universe becomes a natural event, that is, it is part of a physical process described by physical laws, then sitting down in this nothing region before the universe, we must have the laws of physics, or the laws of nature. And so this leads me to, quite naturally, to a discussion about what are the laws of physics, where do they come from, and why do they have the form that they do. And we'll see how this later, how this has a bearing on how many universes should exist. Now, most scientists simply take the existence of laws of nature, or laws of physics, really, for granted. The hidden assumption that underpins all of science is that the universe is ordered in a rational and intelligible way, that there are laws of nature out there. If you didn't think that the universe was ordered, you wouldn't embark on the scientific enterprise in the first place. If it was just a haphazard conjunction of events and processes with no systematic order there, then doing science would be a pointless exercise. And if it wasn't rational, if you couldn't come to understand it through reasoning and experiment, again, you wouldn't embark upon science. So there is that assumption that all scientists make, that the world is constructed in that manner. And the best way I can describe is that there is a scheme of things that human beings can discover, they can come to understand, at least in part, how this system works. And as is well known, science is based on experimentation, but that the laws themselves are mathematical in nature, and so it's a mathematical underpinning. The mathematical relationships describe these laws. And so if we suppose that the origin of the universe is something that is law-like, then these laws that underpin it are going to have an interesting relationship in regard to the universe that they describe. Now, because the laws are mathematical, it leads naturally to a discussion about what mathematics is. And let me just say a few words about this. There are really two views of the nature of mathematics. One is that we discover it, that it's out there, that mathematics exists, that a statement like 11 is a prime number is a true statement, whether there's 11 sheep or 11 fingers or whatever it's going to be, or not, that it's simply the case that 11 is a prime number, and it's something that human beings discover about the nature of numbers, and by extension, other mathematical objects too. And so that's one view of mathematics. The other is that mathematics is simply an invention, that human beings construct mathematical objects and relationships and define all sorts of properties and then explore them. And so there's this tension that exists, and it is often said that mathematicians are, I should say that this point of view that it's out there is called Platonism, after Plato. It's often said that mathematicians are Platonists on Mondays, Wednesdays and Fridays, and are anti-Platonists, or whatever the word would be, for the rest of the week. So here's Plato, looking sufficiently smug, because I think not only are many mathematicians at least closet Platonists, but their colleagues, the theoretical physicists, tend to be steeped in this Platonic tradition. And because the laws of physics themselves are mathematical relationships, they take on the Platonic character of the mathematical objects that are used to describe them. So up here we have this Platonic world, and these things never work, do they, on the night? Never mind. We have the Platonic world you can see at the top, and then the physical world down below, and then this Platonic world, as it were, contains the laws of physics. And so you'll see up here your Newton's laws and Einstein's laws and so on. And these are then, so to speak, projected onto nature. Now, I'm not saying this is the way things really are, but it's the way that most of my colleagues think about the relationship between mathematics, physics, the laws of physics, and the physical world. One way that, of course, not all of mathematics is used to describe physical laws. So it's like a subset, Let me just say that, of course, when we talk about Platonism, we're talking about the laws, about the mathematics, and hence the laws of physics lying beyond space and time. So we might say it's transcendent. And one way we can think about this is that mathematics is like a wonderful warehouse of relationships and forms, and physics uses only a subset, a tiny subset of all the mathematics that's available. So that the various laws of physics you will find in your textbooks are just a tiny part of all possible mathematics. And so what we'd like to know is, why that little bit there, and why not something else? What is it about certain mathematical relationships that commend themselves to Mother Nature? So it's almost like Mother Nature visiting this wonderful warehouse of mathematical forms and relationships and plucking out a few choice bits and pieces, a symmetry group here and a differential equation there. I've even got a picture of her doing it. So that's the sort of party line. At least it is among the people I mix with. I have to say that you can go to physics departments in different parts of the world where they do much more practical, as it were, down-to-earth type of physics, and there sometimes they see the laws of physics somewhat differently. But for people who are interested in things like the origin of the universe, applying quantum physics to the Big Bang and so on, this is very much the point of view. Someone may contradict me at the end of the lecture in questions, I will see. There's another very important point to get across, and I call this Newtonian dualism. It goes right back to the heart of what we mean by the scientific method, and it's absolutely fundamental to the way that scientists think about laws. And this is that the laws themselves are independent of what actually happens in the universe. However violent the phenomena that we may encounter, the laws themselves are completely impervious of it. So the physical states of the universe depend on the laws, but the laws themselves are independent of those physical states. So it goes right back to Newton, the fact you can write down differential equations to describe the motion of matter, and those differential equations are fixed equations. The matter itself can move around and change and so on, but the laws themselves are completely unaffected. So those laws are immutable. So there's this curious asymmetry, you see, between the laws themselves, which are transcendent and immutable and eternal, and the states of the world, which are changing. They're mutable and contingent. And it's interesting to think, where did that dualism come from? What did Newton have in mind when formulating a description of the world like that? And it's very clear where it comes from. It comes from 17th century theology. And here's a couple of quotes that make this very explicit. The first is by Descartes. It is God who has established the laws of nature as a king establishes laws in his kingdom. You will be told that if God has established these truths, he could also change them as a king changes his laws. To which it must be replied, yes, if his will can change. But I understand them as eternal and immutable, and I judge the same of God. So for Newton, the laws were thoughts in the mind of God, and because God was eternal and immutable, then the laws were also eternal and immutable. Spinoza says very much the same thing. Now, as nothing is necessarily true save only by divine decree, it is plain that the universal laws of nature are decrees of God, following from the necessity and perfection of the divine nature. Nature, therefore, always observes laws and rules which involves eternal necessity and truth, although they may not all be known to us, and therefore she keeps a fixed and immutable order. So we see here the theological origin of this idea of fixed, eternal, immutable laws, although a world that can come to change. So how should we then think of the laws according to this conventional viewpoint, which I'm going to challenge in a moment, this conventional viewpoint? We think of them as imprinted on the universe from outside at the moment of its birth, and we can see the stamp, and if you like, there is the maker who's leaving the laws are like the maker's mark. Boom, that's the universe, those are the laws, and they don't change, whatever happens. Well, I can remember as a student always questioning the fundamental assumptions of science and wanting to know, like, where do these laws come from? Why do they have the form that they do? And I was always told to be quiet. That's not a scientific question. Just get on with the job. The job of the scientist is to learn the laws and apply them, not ask damn fool questions about where they come from or why they have the form that they do. So circa 1965, the laws of physics, nobody really spelt it out like this, but that's what it was implicit, that they were absolute and immutable laws, universal, eternal, infinitely precise. That's an important point. Nobody said these were sloppy laws that had rounding errors or anything like that. Infinitely precise. Existing in some sort of otherworldly Platonic realm, transcending the actual universe, and then imprinted onto the universe at the moment of its birth and immune to any subsequent change. What do we think about these today? Is it legitimate to ask where these laws of physics come from? Well, some people think it is, but some people don't like that question. One is often told that these laws exist reasonlessly. They have to be accepted as a brute fact outside the scope of science. It's not a scientific question, and you should not be asking questions of that sort. I'm very grateful to Sean Carroll for just a year ago making this very explicit. So he says, there is a chain of explanations concerning things that happen in the universe which ultimately reaches to the fundamental laws of nature and stops. At the end of the day, the laws are what they are. But that's okay. I'm happy to take the universe just as we find it. In other words, we accept the existence of these laws as a brute fact. It's it. That's it. We can't dig any further. That's the end of the story. I'm not very happy with that, for one, but I think many of my colleagues would like to feel that we would like to understand why the laws are what they are, and maybe even have a theory of laws, or have a theory of understanding at least why we observe the particular form of laws that we do. Now, obviously, if we're talking about how the universe came into existence as a natural process, we have to assume that the laws which governed the origin of the universe have some sort of transcendent existence and can bring a universe into being from nothing. So the laws are somehow there, if you like, and they lead to the emergence of a universe. And now we reach the crucial point that ties with the title of the lecture, that would be a funny sort of law that acted only once. Can there be a law of nature that brings a universe into being just once? It would seem that if a universe can come into existence from nothing as a result of a physical process, if it can happen once, it can happen many, many times, maybe an infinite number of times. So that leads naturally to the conjecture that there isn't just one universe, but a multiplicity of them. And so raises the question, just how many universes are there? Or how many creation events, if you like. Well, let me take them one by one. 0. Well, I think we can rule that one out on the basis of observation. We know that we've got at least one universe. So 1, okay, that's the conventional point of view. There's one universe, and this is it. And you could either take the point of view, well, it's a mystery, that's how it came to exist. You might think, well, perhaps it really has always existed, and we've just got it wrong, with the Big Bang being the ultimate origin of things. Maybe either of those. But let's go on. What comes after 0 and 1? Well, 2. Might there be 2 universes? Well, that's not such a daft idea, because we have examples in nature of pair creation. This is a picture of an electron-positron pair being created. So this is where a particle and its antiparticle come into existence, in this case right here. Might we imagine something similar for universes? Could there be a universe and somehow an anti-universe, a pair creation of universes, maybe one with properties like the direction of time being reversed from that of the other? That would be a natural sort of symmetric state of affairs. And in fact, it's one that Andrew Chamblin would have appreciated, I think, because he alludes to it in his paper with Gary Gibbons. So the idea that there may be two universes is actually a very old one, and a lot of people have toyed with that notion that there could be something like a universe of matter and a mirror universe of antimatter, or with the time reversed, or some sort of symmetry that would, if you put the two together, would in some sense give you nothing. So if you're starting with nothing, and then you have A over here, then minus A over there, keeps that sort of symmetry. So that's a possibility. Let's go up a bit. I won't go to 3 or 4. Let's go straight to N. What could N be? Well, unless you've been living on another planet, you'll probably know that our best attempt to understand the sort of processes that may have brought the universe into being, and certainly that characterized its very early stages, is described by something called string theory, and this is the best I can do to illustrate string theory. What is string theory? It says that the entire universe is built out of little loops of string that wiggle around. And it sounds sort of absurd put that way, but it does hold the promise of giving us a consistent theory of not only all matter, but all the forces that act between particles of matter, and maybe space and time as well. Now, string theory is still work in progress. It's immensely difficult, both mathematically and conceptually, and there's a small army of theoretical physicists working on it at this time. And there's some disagreement as to how many different sorts of universe it describes. When string theory was first being formulated, the hope was that it would lead to a description of a unique universe, this universe, our universe. But many people working in string theory believe that, in fact, it leads to a description of not just one universe, but to a stupendously large number. And to put a particular figure to it, this is Lenny Susskind's figure, 10 to the power 500 possible universes. And the way of describing this is that there could be like a landscape of possibilities, and that landscape could be populated by actual examples of this sort of stupendously large number. That leads to the concept of the multiverse, the notion that what we've all along been calling the universe is just an infinitesimal fragment amid this vast and more elaborate assemblage of universes which is collectively carries this name, the multiverse. Now, for this to have any traction, these universes have to differ from each other, and according to string theory and some other, it's not just string theory, some other rather basic principles in theoretical physics, that if you have a universe emerging from a hot Big Bang, it's likely to have many, many different low-energy manifestations. So that what we've been thinking of as the laws of physics as absolute and universal and totally fixed turn out to be, as Martin Rees puts it, more like local bylaws, valid in our particular cosmic region, which when I say cosmic region, I'm talking about something that could be very, very much bigger than even a Hubble volume, even this volume of space that the Hubble Space Telescope can access, that it could be enormously big, but nevertheless a finite patch. And so that if you don't like the laws of physics here and you go to the universe over there, maybe you think it would be nice to have electrons a little bit heavier, you go over there and you'll find a universe that's got that. Or you think gravity should be a little bit weaker, go to a universe over there, it's got that. So all possibilities, or at least 10 to the 500 of them, are instantiated somewhere. There's a sort of vast cosmic smorgasbord of different possibilities out there. Why should anyone want to believe in that? Well, some people think it leads to a ready solution of one of the long-standing puzzles of relating cosmology to the existence of cosmologists who observe the universe, and this is the Goldilocks enigma that often expressed by saying, why is the universe just right for life? What I mean by that is that if we were to change the laws of physics a little bit, maybe not very much, then it seems that life, at least as we know it, may not be possible. Now, in case that sounds a bit mysterious, let me just give you a couple of examples. I don't want to dwell on this because there's not a talk about this particular topic, but just to show you, Well, first of all, the best way of thinking about this is imagine you didn't like the universe. As I said, you'd perhaps prefer electrons to be a bit heavier or gravity to be a bit weaker. So imagine playing the role of God, and in front of you is the designer machine, and it's got little knobs on, and you twiddle this knob and you make electrons a little bit heavier, and then you twiddle that knob, you make gravity a little bit weaker, and so on. You might wonder, how many knobs do you need to describe the universe as we know it? And the answer is 30-something. In our present state of knowledge, there are 30-something, as we would say, undetermined parameters in the standard model of particle physics and cosmology that suffice, once you fix their values, suffice to describe the world that we observe. Nobody believes that all these parameters are really unconnected. Maybe deep down, at a deeper level of theory, they will be connected, but we don't know how many. But we can imagine twiddling those knobs, and it does appear that, at least for some of those knob settings, even the slightest little twitch would be lethal, literally lethal. It would lead to a universe that could not permit the existence of life. And so that's long been a mystery. In fact, Fred Hoyle, whose name I shall invoke again, once described this state of affairs by saying that the universe is a put-up job. So it does have that sort of air of contrivance to it. Now, the great thing about the multiverse is that we can readily explain that apparently contrived nature of the universe in relation to the existence of life. Because, of course, if you have 10 to the 500 different possibilities out there, maybe an even larger number, then somewhere, just by chance, all those little knob settings are going to come out right, and then those will be the universes where life will emerge, and beings like ourselves will look out and say, isn't it amazing how things have been put together? Because, of course, we could not live in universes where those knob settings were any different. Here's just a simple example of a knob setting. If you know anything at all about basic physics, that you know that the atom, the nucleus of the atom contains neutrons and protons, and the neutrons and protons are almost exactly the same mass. But it turns out the neutrons are just a tiny bit heavier, about 0.1% heavier than the protons, but it's an absolutely crucial difference because neutrons are a little bit heavier. In isolation, they decay. They're unstable. After about 15 minutes, they decay into protons. Now, that's okay. But if it was the other way around, if the great cosmic designer had botched the knob twiddling and made the proton a little bit heavier than the neutron, that would be disaster, because then the protons would decay in about 15 minutes into neutrons. Now, does that matter? It surely does, because without protons, you don't have charged nuclear particles, so there are no nuclei. Without nuclei, there are no atoms. With no atoms, there's no chemistry. No chemistry, there's no biology. So the existence of beings like ourselves hinges upon the neutron-proton balance like that. I can whiz through some other examples. As I say, I don't want to belabor this. I'm going to skip right over this one. This was Fred's example of the production of carbon in stars. Many people here will know this story. I'm going to skip over it for lack of time. Carbon is the life-giving element. You've got to make carbon, but you also have to get it out into the interstellar medium so it can be scooped up into planets and eventually the bodies of living beings. Getting the carbon out of stars depends on the stars exploding and disseminating them around, and this depends on getting certain knob settings right as well. But perhaps the most dramatic example of the knob settings being just right comes from this picture here. This is a picture of the early universe. It's a heat map of the early universe called WMAP, Wilkinson Microwave Anisotropy Probe. And this is what the universe was like about 380,000 years after the Big Bang. And the red bits are the hot spots and the blue bits are the cold spots. Overwhelmingly, the temperature of the universe, I should say that this is like a fading afterglow of the Big Bang. It's a heat radiation that fills all space. The overwhelming first impression is it's incredibly smooth across the sky, but on closer inspection you find that there are these tiny variations. Now the point here is that if these variations had been bigger, then as the universe evolved, its large-scale structure would have developed into monster black holes instead of galaxies and clusters of galaxies, because the hot and cold spots represent slight variations in density of of material. And where the material is dense, it drags in more material and forms clusters of objects. And if those clusters get too big, they become black holes. So if you had the actual density contrast is about 1 part in 10 to the 5. If it was 1 part in 10 to the 4, we'd have monster black holes. On the other hand, if it was 1 part in 10 to the 6, then probably galaxies and stars wouldn't have formed at all. So either way, it would be bad news for life. So these are the sorts of things. And as I say, I'm not going to belabor it. The main point I want to make is that it's circumstantial evidence in favour of some sort of multiverse. And so that's the prime reason I think that it's a fashionable idea. Now, does that answer all our questions? And in particular, does it tell us how many universes there are? Well, we obviously have some problems, because it's all very well saying that we have all these universes, but does that tell us where the laws of physics come from and why the laws of physics have the form that they do? Well, it doesn't really, because to get all these universes, you need, for a start, a universe-generating mechanism, and here's one. So we need some way of making universes. So I've explained that if you have laws of nature that can make a Big Bang, make a universe out of nothing, that this law could make other universes, but there has to be this set of laws, this mechanism, this means of generating these universes. Otherwise, this makes no sense. And then the question inevitably is, where do those laws come from? Well, do we have a mechanism? Well, there's one that is very popular. It's called eternal inflation. This is due to Andre Lindy at Stanford University. This is a method of populating the landscape of string theory with universes. And so it would take me outside the scope of this lecture to go into a full description of eternal inflation. But the essential idea is that very early on in our universe, just after the Big Bang, in the first split second, the universe was expanding exceedingly rapidly and exponentially. That is, it was doubling in size in a very short period of time. And this frenetic, in eternal inflation, this frenetic expansion is always going on somewhere in space. But in regions like ours, it stopped and has been replaced by a more sedate type of expansion. But if we stand back and took a God's eye view, we would see that our universe is just one of these bubbles, if you like, a Hubble bubble, in fact something much bigger than a Hubble bubble, amid this frenetically inflating superstructure. And eternal inflation, because it describes a process of nucleating new universes, so that when we think of the Big Bang, was it the only Big Bang? According to eternal inflation, no, there were many Big Bangs scattered throughout space and time, and there are always Big Bangs going on somewhere. And the technical term is nucleating new universes from this inflating superstructure. So this is one possible universe-generating mechanism. But of course it comes with a lot of baggage, a lot of physics baggage, a lot of meta-laws, if you like. Specifically, in the case of eternal inflation, the universe-generating mechanism assumes quantum mechanics, in fact quantum field theory, relativistic causality, and a number of other fundamental features of physics. So to have the universe-generating mechanism, you have to have that existing ab initio. So again, we have to appeal to some sort of transcendent laws of nature to drive that. If it's going to be a string theory description, we need some sort of super law, could be a string theory Lagrangian, we need a space-time for it to act in, and a whole bunch of other stuff that is of a technical nature I won't get into. So we can always ask, okay, we can believe that the universe, the origin of the universe, can be brought within the scope of physical law, and we can always ask, where do the physical laws come from? And we can say, well, there's a selection of laws, and so all possible laws may be out there somewhere, but we still need meta-laws and the universe-generating mechanism to make all this happen. And we can just move the whole set of problems up a level from the laws of physics in one universe to the meta-laws in the multiverse. And what we'd like to know, ultimately, is there a reason for all this? Is there a reason for why the meta-laws are what they are? Or do they exist reasonlessly? That is the universe or the multiverse ultimately absurd? Or does it hang together in some coherent way? I'll touch on the answer at the end of my lecture. Well, a possible answer. So I've gone from 0 to 1 to 2 to n, which is a big number, 10 to the 500. Why stop there? What about infinity? Could we have worlds without end? Might there be an infinite number of universes? The problem about infinity is it does lead to some weird, indeed even paradoxical notions. And you get into this even if you have a single universe which is infinite in extent and homogeneous on average. And one of the things you get into is the fact that, to put it crudely, in an infinite universe, anything that can happen, and will happen infinitely often. And among the things that will happen is that somewhere, way, way over there, will be a duplicate of you. That is, that there will be duplicate beings. And if you'd like to know how far you have to go, it's, according to Max Tegmark, 10 to the 10 to the 29 meters in some direction or another. So you're not like to run into your other self. But nevertheless, if the universe is truly infinite and truly homogeneous and the laws of nature are uniform, you are assured that out there will be a duplicate of you, and indeed, by extension, an infinite number of duplicate beings. In fact, there'll be an infinite number of duplications of this entire audience. And then, if you go further, there'll be an infinite number of Earths, indistinguishable from this one, and even an infinite number of Hubble volumes of universes that we can see, identical copies, infinitely scattered throughout space. To get a Hubble volume, by the way, you need to go to 10 to the 10 to the 120 meters. So that's 1 followed by 10 to the 120 zeros in meters, well, centimeters. It doesn't really matter. A long way, anyway. So that's the problem about an infinite number of universes. But it gets worse. The problem is that this touches upon the nature of reality. When you say to people, well, there could be duplicate beings, they always want to say, well, which one's the real me? And so the question about what is the real me is particularly difficult once we take into account the possibility that consciousness and that our observation of the world is something that is essentially a physical process. It's something that's happening up here in our heads. And I think we all know that the claims being made that maybe within a few decades, but certainly we imagine within a few millennia, it should be possible to make something like artificial intelligence or artificial consciousness. It should be possible to make, though surely not in a computer of this sort, make entities which share with us the nature of consciousness and self-consciousness and being able to be aware of the world. And so the difficulty is, if you can simulate a being in a computer, then you can simulate a world for that being to experience. And all this could be done in silico instead of in the real world. And of course, if you can do it for one being, you can have a whole community of beings, in effect, digitally simulated, thinking that this is the real world, because it begs the question, are we the result of a digital simulation in some other universe by some other sort of intelligence? So, of course, it's all very familiar from the Matrix series of movies. And the difficulty here, you see, for the multiverse is the following, that once you have a universe that has a planet that has beings sufficiently advanced that they can start making duplicate virtual realities, if you like, rather than duplicate, the virtual worlds, fake worlds. The fake worlds very soon proliferate to outnumber the real ones. Fake worlds are much cheaper than the real thing. You know, if you were to make a universe like a Hubble volume, it would be a very expensive enterprise. But if you were to simply simulate it, particularly just simulate a little portion of it, so it doesn't matter now that we can't see the moon. We assume it's there. So it's very, very much cheaper to simulate fake worlds. So we can imagine that if we take the multiverse seriously, then in addition to all the real universes which are out there, there are going to be an even greater number of fake universes. And it gets even worse, because the thing about digital simulation is that a digital computer, by its very nature, can simulate another digital computer. So a Mac, for example, can simulate a PC. And so if you can, on a gigantic computer, simulate a world, then you can simulate a computer in that world which can simulate its own world and its own world, and so on. And so we have this vast tower of nested universes within universes, and it really, begs the question, where is reality in all this? Is there a basement universe, or is it just an unending tower of simulations within simulations? And so once you get into this multiverse game, you're down this slippery slope of where is reality in all this lot. Those people are interested, by the way, you should know that Nick Bostrom at Oxford University has a website called www.simulationargument.com. You can go there to find out more about this bizarre topic. This is sort of getting to the heart of the message I want to convey, and then I'll wrap things up. What we're talking about here is existence, isn't it? How many universes are there? How many universes exist? What do we mean by universe? What do we mean by exist? I've been talking about how the Goldilocks enigma could be explained by a multiplicity of universes with the laws varying from one to the other, and only a tiny subset being consistent with the existence of conscious beings. And that's a good way of separating the set of all that actually exists from the set of what can be observed. Obviously, we will observe only a subset of all that can exist, so this is just hopeless, this thing. I should have ordered the cane. I was offered it, but I thought this would work. Anyway, you can see what I mean. This word anthropic, it's just a provocative word that is used for the type of reasoning that we will see only universes consistent with the existence of observers. So that's okay. That can divide, that blue line there, that boundary A, can divide those universes that can be observed from those that can't. And of course there are probably many more. The yellow bit would be much bigger than the red bit. There'd be many more universes that could not be observed than those that can be. But it tells us nothing about that other boundary between all that actually exists and all that could conceivably exist. You see, in the existence game, you've got all possibilities, and then you've got what actually exists. And the question is, does what actually exists exhaust all possibilities, or is it less than that? That's a real problem. I call it the problem of the rule. There are really only two natural states of affairs where we don't need to get into this problem, where there isn't a boundary problem. One is that nothing exists. Well, we've already ruled that one out. And the other is that everything exists. Maybe everything that can exist does exist. Not just an infinite number of universes, but an infinite number of all possible universes, every possibility. Now, Max Tegmark, whose name I've already invoked, cosmologist at MIT, he's actually proposed this, that not only is there an infinite number of universes, but all conceivable universes actually exist. Now, by conceivable, he means all possible mathematical structures represent an actually existing universe. And you might say it's a somewhat impoverished definition of existence, basing it on mathematical structures, but it's exactly what you would expect from a mathematical physicist. But we might like to, walk around the university and talk to other people, and we might want all possible artistic structures, all possible moral structures, and so on. It goes on and on and on. But we could imagine that everything that can exist does exist. But I don't think many people like that. I'm sure most people here feel that although there may be a lot of things that exist, that what does exist falls short of everything that is possible. And so that means there's going to be a rule or a division between those things that actually exist and those things that could exist but don't. And so that begs the question, well, where does that rule come from? And who gets to decide what is dignified with existence and what is merely possible but not actual? What is it that actualizes the subset of things that really exist and separates them from those things that might have existed but don't? So there has to be a separation. So Stephen Hawking has described this more elegantly about where this rule comes from. What is it that breathes fire into the equations, he says, and makes the universe for them to to govern. So it's a fire-breathing actualizer that selects from the set of all possible universes, the subset of universes that can exist. Well, of course, we don't know the answers to any of these things, but it shows you the territory we get into. So this is reminiscent of the famous Tower of Turtles, the lecture being given, somewhat of this nature, in which it seems always to be a woman who stands up at the back and says, I know how the universe is put together. Pray tell us, says the lecturer. Well, it's the world is standing on the back of an elephant, which is standing on the back of a turtle, to which the lecturer replies, and what is the turtle standing on? You can't fool me, it's turtles all the way down. And so we get into this problem that if we're after an ultimate explanation of existence, then what we're really after is we either get ourselves into an infinite regress, or we're after a levitating super turtle that somehow holds the whole tower up. And that levitating super turtle either has to somehow explain itself, self-explanatory, or ultimately existence is absurd. Because if there is no explanation for why things are the way they are, then ultimately existence is absurd. And we have distinguished people prepared to argue for either. There's a long tradition in theology for self-explanatory universes or self-explanatory beings, the concept of a necessary being. So they've had hundreds of years to come up with the idea of a being, the non-existence of which is a logical impossibility. It's not clear to me that a necessary being is a coherent concept, but at least it's a nice try. Or we could just say, like Sean Carroll, it's all absurd, we just accept it as a brute fact. There is another possibility, however, that if the universe were to be self-explanatory, then this sort of logical dependence, which is the standard one, which is underpinning everything, is mathematics. The laws of physics are mathematical forms, that the universe comes into existence as a result of mathematical laws, matter comes to exist as a result of those laws, and ultimately life and mind, beings like ourselves who reason, look, observe, trying to make sense of it all. We see this as a sort of great chain of being, a linear chain, but there's no reason why it couldn't form something a bit more like a loop, some sort of self-synthesizing, self-explaining reality where the universe, the laws, the observers, the mathematics are all part of a sort of mutually supportive, mutually explanatory scheme. You see I'm waving my arms because that's all I can do because I can't write down this scheme. One of the things, though, if we wanted something like that, you'd have to abandon is that Newtonian dualism, that asymmetry between the laws and the physical states. If you want the universe and its laws to be part of a self-explanatory package, then you would have to allow the laws and the physical states to be mutable, to affect each other. So it's more like a universe, instead of the laws being imprinted on it at the moment of its birth from without, in that, like the maker's mark, it's more like the laws, the universe self-organizing its laws. It's more like a self-organizing or emergent system where the laws and the universe emerge together. It's more like a turtle loop than a tower of turtles. And I have to say, everything I've been saying is far from new. In fact, pretty much exactly recapitulates 30 years on what John Archibald Wheeler, one of the great and most entertaining theoretical physicists of the last 50 years, was articulating, that he was fond of saying there is no law except the law that there is no law. So he wanted laws, universe, everything to come out in some self-consistent, self-explanatory manner. Well, at this stage, this is really more an agenda to be implemented than any sort of theory. But I myself think that the idea of a single universe which is self-consistent and self-explanatory is better than a tower of turtles or an infinite number of universes. But to conclude with answering the question I started with, how many universes are there? Well, if I told you there were 847, it's all done, you'd go away thinking, well, that was a ridiculous ending to the lecture. Why would there be 847? And I think that's a very good point. It's hard to see why. we can imagine that there's one universe. I think we can imagine there are two. I quite like the idea of the universe and the anti-universe in some sense. But if it's not one or two, then I think it has to be infinity. So in a way, you pays your money and you takes your choice here. It's got to be 1, 2, or infinity. And all of them have existential problems. They all lead us into paradox or a Tower of Turtles or something that baffles us. And maybe it will forever be the case. It may be that simply science or rational reasoning has reached its limits. The human mind, after all, has evolved for survival in the proverbial jungle. Evolution builds our minds in the same way as it builds our bodies. And it may be that we simply don't have the appropriate conceptual framework to grapple with these ultimate questions. I've spent most of my career kicking them around. I don't give up easily, but I'm the first to admit that it simply may be that it will forever lie beyond our ken. So I'd like to finish, because some of you might think that this lecture's been a bit speculative, so I'd like to finish by bringing us down to earth and quoting another great Cambridge physicist who once said, don't let me hear anyone use the word universe in my department. This was Lord Rutherford. One dreads to think what he would make of what I've been saying about the multiverse. Anyway, thank you for your attention.
So, although he's willing to take questions, so are there any questions? Could you speak up?
I will repeat the questions, but Right. So let's not go too far down the path of the nature of consciousness, one of the deepest mysteries of science and philosophy. But so the question is basically that if we can make some sort of physical system, and I've used the word computer, but that should be in scare quotes, because it may be nothing like what we understand to be, this type of computer. But the point is that if consciousness has a physical basis, then in principle we can simulate that. After all, we could surely build a human being atom by atom in principle, and then we'd have a conscious entity. And so I'm assuming that consciousness is not some sort of supernatural phenomenon that's glued on to a physical system, but it's something that emerges from natural processes by some still deeply mysterious connection between things. And so therefore, in principle, we could build it. In principle, yes, you'd have a conscious being, and then we would be faced with an ethical dilemma about pulling the plug on this being. And I'm a bit involved in something called the Blue Brain Project, which is run out of Switzerland. There's a computational neuroscientist, Henry Markram, who wants to simulate the human brain. This is not the same as artificial intelligence, where you make a sort of cartoon version of the brain. This is to simulate actual neurons and actual interconnections up to 10 trillion synaptic connections, and with 500 parameters per neuron. And so this is a very ambitious project, like the Human Genome Project. It relies on Moore's law. It would take probably years, if not decades, to implement. But in principle, we could simulate a brain at that level of detail. And then the question is that simulation a conscious being? And I think it would have to be if it's a faithful enough representation of a real brain. So I think at some level you're going to have to inevitably say, yes, we're dealing with a real brain. As far as free will and Schrödinger and quantum mechanics is concerned, fascinating questions I spend a lot of time thinking about. I'm working at the moment with Yakia Aharonov, one of the founders of quantum physics in the modern era, who has some new ideas about what we could mean by the notion of free will in a quantum system, but I think it's far from solved, and we don't really know how it fits in. And most of my colleagues would say free will doesn't exist anyway, it's just a feeling we have. No, it's not hidden variables, nothing connected with that. Anyway, I think we better take another question. Yeah, the young man in blue. How much is my job? You'd like a job like mine, would you? Well, I have to say that when you ask that question of an academic of my age, then the answer is 95% of the job is horrible administrative things, sitting on committees and writing reports and grant applications and so on. But factoring that out, then because I wear a number of different hats, you probably picked up earlier that I do physics and cosmology, but I also do astrobiology, and then there's all this sort of wishy-washy philosophy, mumbo-jumbo, as my friend Mike Duff calls it. Then the physics and philosophy is, the physics and cosmology is all about equations and solving equations. So it's really mathematics. The astrobiology is not so much about mathematics, and that's much more interacting with real people in actual labs, and my particular interest is in the possibility that life on Earth may come in more than one form, that there may be in the microbial realm an alternative form of life right here on Earth. So that's something I'm working on at the moment. And that's a very different type of thing. And then the philosophy is something that happens over tea and coffee, or in the middle of the night. And so these are, many physicists and cosmologists are just amateur philosophers, so we love to sit around and talk about these things. We have no competence to do so whatsoever. I have no qualification. Well, I have a PhD, of course, but it doesn't really mean I'm a qualified philosopher. And so I'm always told off by my philosopher friends that 99% of what I say is complete garbage. So I think Stephen Weinberg expresses it very well in his book, Dreams of a Final Theory, that we physicists, he said, have a sort of rough and ready philosophy, and I think we sort of get by on that basis.
If there are two universes, could we not find evidence for the other one?
It depends where it is. Now,
Antimatter would have to be separate.
now one way, and Fred Hoyle, was most ideas he thought of in one form or another. So he liked the idea that the universe was expanding and had matter in it and time sort of running this way. But if you went back to some time in the remote past, it would all switch around, and then there'd be a universe that but from our point of view would be contracting, but from its point of view would be expanding. The arrow of time would be reversed and it would have antimatter in. And so that universe is like, it's connected to ours, but it's in the infinitely far past. So we can't get at it because it's already happened a long time ago. And beings in that universe would think we're in their far past. So it's sort of inaccessible from that point of view. This idea of, sort of a nucleation of two universes somehow separated, well, it then becomes, you have to be very careful about the definitions. If this is part of a sort of eternal inflation type of model, then there's still this inflating superstructure, and these two universes could be conveyed apart much faster than they're expanding, so they will never intersect. But we can imagine other models where they do intersect. So, I mean, basically, there are all sorts of ways you can do this. But I can't resist, I mean, I don't take this seriously, but I remember when I was a student, there was a great consternation about the discovery of a particle called the kaon, which seems to decay in a way that violates time reversal symmetry. So if you run the movie backwards, the laws that apply in the backwards universe don't seem to be the same in the forwards universe. And nobody quite knew what to make of that. But I always remember a lecturer of mine. I was at University College London as a student. This lecturer, I still know him, he's a personal friend now, he's Russell Stannard, publishing a paper, I think it was in Nature, in which he conjectured that the way that the K-meson decayed in this funny manner was that there was another universe with time running the other way. It was just possible for a particle to slip through from our universe into this time reverse one, and then back again, and that's what led to this peculiar effect. So, all these ideas are out there. And of course, if you read science fiction, because most of what I've been saying here is really science fiction. If you read science fiction, you'll see all sorts of other possibilities for universes and anti-universes. Bewildering.
No, bewildering. No? A little inefficient.
Ah.
So one of the projects I'm working for does involve real-time simulation very much like yours. And you would need a power plant in order to, in future, simulate the brain. It's so incredibly efficient.
Right. That's right. We get by on 3 meals a day, but to simulate that, somewhere I've got a lecture where I actually give the power output necessary to simulate a brain. It is enormous. Yeah. No. But you see, the point is that in a multiverse, there's always a universe somewhere where there will be sufficiently advanced beings that all these technological problems get solved. So even if in most universes the technological societies bite the dust before they ever get to the stage of being able to simulate communities of beings, some of them somewhere are going to do so. And then that unleashes this vast matrix-like proliferation of fake universes.
But that doesn't seem to solve the energy problem. They have to create energy.
No, because in principle you can have a quantum computer, for example, then it's in principle dissipationless. Now there are error correcting issues associated with that, but you can have a perfect computer that doesn't, a reversible computer that doesn't dissipate energy. So in principle, yeah. Whether in practice. I haven't worked through the thermodynamics of it, but that would be a really good problem. Could you in principle do this?
Let's say you created a compressed version where you've hidden away some of the details, used simple laws, and you've created virtual views.
Right.
But that sort of virtual view cannot simulate the universe more efficiently. The only way that they can do it is less efficiently.
Right, diminishing returns within these nested universes. Yeah, it's a point that's been made to me by John Barrow, in fact. Yeah. I think that's right. And it would be nice to prove some theorems about, just how many universes can you get nested inside each other before you just hit that thermodynamic barrier. What are the ultimate thermodynamic limits to making fake universes? Would be an excellent PhD project for someone. Any takers?
You said one more?
Yeah.
The middle? The middle?
Yeah.
You touched on your thoughts on the fine-tuning of universal constants.
Right.
Basically was circumstantial evidence for multiverse theory.
Right, so some people say, well, the fact that we live in a universe which seems to be fine-tuned suggests that there is a multiverse. So other people think there's other explanations. Well, I think I agree with what you were just saying. So if we have a multiplicity of universes with variations of all these parameters, the values of which are mysterious, but are necessary in order for there to be life, then it becomes no surprise that we find ourselves existing in a universe, or region of space at least, in which the parameters come out right for life, because we couldn't obviously live in a biohostile. It's got to be a bio-friendly patch. It can't be a biohostile patch by definition. And so that's a bit like saying we live in a very atypical part of this universe, namely the surface of a planet. Most of the universe is near empty space. We don't live in near empty space. Is that a coincidence? Is there something weird about that? No. We've selected it because we couldn't live in outer space. We live on the surface of a planet because that's where you get life. And so it becomes a selection effect. And the question is, can one project that selection effect onto the universe as a whole or into this multiverse? Now, some people really hate that idea. They hate it because they think it's a cheap way out and that we should be attempting to explain the values of these parameters from some fundamental theory. And I think that's right, we should. But on the other hand, it's quite clear that some features of what we observe in the universe are a result of selection effects. And it's anybody's guess as to which of those still unexplained features are selection effects and which are simply, which will one day, at least in principle, could be explained by some fundamental theory. We don't know. And so it's best to be open-minded, and that's the attitude I take.
So I think that's a good time to bring things to a close. So I hope you'll join me in thanking Professor Davies for giving us a very interesting, thought-provoking third Andrew Chamblin lecture.